Can you share my screen now? Okay, sorry, can you see my screen?
Yes, I can. If you could please make it full screen. Yeah, perfect.
Yes. Yeah. So thanks a lot for giving me this opportunity of presenting my results of my research on thermodynamics of heat engines. This is a joint work with Marcin Łobejko and Michał Podleski. We are all from ICTQC in Gdańsk. So let's start. And please interrupt me, feel free to interrupt me whenever anything is not clear. So this is the general scheme of a heat engine that you probably are familiar with. Even if you are not working in thermodynamics, then sure you remember it from a primary school. The idea is that you have a working body that here is in the middle, and you have two thermal baths with higher temperature TH and with lower temperature TC. And you have a heat flow from the hotter bath to the colder one through the working body that undergoes some processes, as a result of which part of this heat flow is converted into work, so in a useful form of energy. And as usually, we are interested in calculating efficiencies of these processes and also powers associated with these processes. This is a very old idea, and of course we are all familiar with applications of these devices. But now, as we are able to create smaller and smaller systems, we are not restricted to macroscopic representations of this scheme. So it no longer has to be a representation of a power plant in which steam as the working body is heated, and then it goes through the turbine, it generates electricity, and then what remains, the steam goes to the cooler and the cycle closes. Now, instead of these tons of steam in the energy power plant, it can be a qubit in our laboratory. And this thermal baths, it no longer has to be some boiler heated by burning coal or other energy sources, or a large amount of water from the lake or river in case of colder reservoir. It can be some bosonic or fermionic bath with a selected couplings such that they match the energy difference in the working body and give the energy in the form of heat. So the idea of going from macro scales to micro scales in building heat engines already dates back to 50s. In 1951-59, there was this paper of Scoville and Schultz-Dubois. They realized that, in fact, the masers, so the three-level systems, can operate based on coupling to thermal reservoirs. The idea here is that you have, again, thermal reservoirs of different temperatures. This one is higher and this one is lower. And the coupling between the working body, the three-level system, and the hot reservoir is adjusted to the energy gap between the first level and the third level. So here, because this is supposed to work in thermal equilibrium with the baths, so the population in the steady state, the ratio between population on the level 3 and level 1 would just be given by the Boltzmann distribution corresponding to the hot temperature. And we can think in the regime that this temperature is really high, so then the population on the third level will be almost comparable to the population on the lowest level. But then we also have a coupling to the cold bath, and this coupling is adjusted to the energy gap between the third and the second level, and this temperature can be really cold. And therefore, there will be a big difference in populations between level 3 and 2. Here you have this profiles drawn at the same place. And clearly there is a regime of temperatures in which the cold temperature is so low compared to the temperature of the hot reservoir, such that you have the inversion of occupation. So there are more, there's more probability of finding the state on the second level than on the first level. And if you remember from solid state physics, this is the situation that lasers also utilizes to produce radiation. In this case, this is Maser, so this is all in the frequencies of microwaves, and we will have the microwave stimulated radiation. So we will have the inputting beam of the frequency corresponding to the gap between levels 2 and 1, and we will have the amplified radiation. And this amplification is because there are transitions from level 2 to 1 that utilizes this inversion of occupations. And it's very simple to calculate the efficiency of this process. Close to the equilibrium, you just have the outgoing beam with the frequency that is corresponding to this energy gap. And this is just omega h minus omega c. This is this thing, and here it should be omega h. So the incoming beam from the hot reservoir, and we have the efficiency that is opto efficiency. So a very classically often observed efficiency. And the condition for the inversion of populations implies that this, in fact, cannot be higher than the Carnot bound. Okay, so here we have a small dimensional system, but many things happened since 1959, and now we are in 2021, and we know much more. We not only are able to describe processes happening with a low dimensionality of the working body, we can also actually investigate the quantum effects associated with it. So we can separate the engine into many parts, and we can ask what are the results of the possible quantum correlations that are present. We can also ask for the effects of correlations between the working body and the storage battery. We can imagine we would like to charge a battery, the external reservoir of energy, as a result of the working of the engine. And as these are now quantum systems, the correlation effects may influence the working of the machine. But there are certain things that we are sure. The first one is that for sure we cannot violate any of in the classical limit, we cannot violate any laws of thermodynamics. So the Carnot efficiency bound still applies as long as you do not manipulate the reservoir. Of course, when you use squeezed states and play other tricks, then you can increase efficiency, but this is rather associated with using this extra resource, using this extra energy that you already put into the reservoir in order to prepare it. There are some effects that are detrimental actually to the use of thermal machines in microscale, and these are associated with, again, correlations that develop between the subsystems, and this is dubbed quantum friction. But on the other hand, in certain regimes of operation of these machines, in the weak coupling regime, and simultaneously when the driving of the system is weak, it can be shown that actually correlation help. They do not help in terms of efficiency, but they help in terms of power. And this is a quite recent experiment from 2019 in nitrogen vacancy centers in Diamond. And here you can see a scheme very similar to the one that I showed you for a Maser system. We have 3 spin energy levels. two of these transitions between level +1 and 0. This is associated with optical pumping. So this is connected with the heat bath. It can be with the hot bath. It can be described as being connected to the hot bath. And then you have the excitation between level 0' and 0, also in thermal equilibrium with the bath of different temperature. And in this experiment, they actually performed the amplified emission, stimulated amplified emission of radiation, but they measured, the focus here was to measure power in this experiment. And the figure of merit here was the total action. So the total action, it corresponds to the product of time of the experiment, time of the cycle, times the norm of the super operator acting on the system. So this is somehow quantifying how strong was the action of the driving and of the coupling to the environment. And the classical description was giving a limit on the acquired power of this outcoming amplified radiation. But the measurement actually showed that for very small values of total action, the power stopped decreasing linearly with the total action, but it's saturated at non-zero level. And this was actually described by theoretical model as resulting from coherences that develop between these 2 out of 3 levels. Without them, the power would be smaller. So this is one of the example of power boost that is attributed to quantum nature of these systems. The last example that I wanted to show is of the trapped ion engine. Here we have another qubit, this green fluorescent dot. It is in the electric trap, and this trapping is associated with the constant potential coming from the voltage applied to these two ends, and also to the time-dependent voltage applied to this electrode, and this stabilizes the ion. The ion is stabilized in the position that corresponds to the shape of the distribution of its wave function. So whenever we will be whenever the ion will be in the thermal equilibrium of one of the laser beam, it will be in one position. But then, as we will add some white noise, which corresponds just to increasing temperature of the environment, then the ion would feel a force and it will stabilize on a different position in this system. And this different position is associated with the difference in energies splitting between its energy levels. This is one of the most recent implementation of nano heat engines. So we have a 2-level working body, and it operates in a cycle that resembles the Otto cycle, as we have a changing variation of the gap, and also the thermalization with different reservoirs. You can see that the efficiency and power are not very impressive, but it worked to some extent. There are, of course, many other proposals based on quantum optics and superconducting circuits. Here, there are some hopes that exploring nonlinearity effects may help in boosting power. Also, it is possible to ask in the semi-independent question about the optimal choices of batteries. So, for example, in this engine, the whole energy that the working body was gaining through interaction with hot and cold environment, it was going to the oscillations of this ion. So it was just oscillating with higher and higher frequency, and it was not giving away its energy to any external storage. It had to be cooled down in order to stay with the same energy after the whole cycle. So ideally, we would like to attach some subsystem that would just that would store this energy from the cyclic oscillatory motion of the working body. And the system is what are the most optimal designs of these systems. Most recently studied are disordered spin systems and some combinations of superconducting circuits and optical systems. So these are just examples, and there's a need for a general description that would put some bounds on performance on the machines that would just tell us what is the role of correlations, for example, between battery and the working body. What are the bounds on power? What is actually the role of dimensionality of the working body if we increase it from 2 to 4, how better the performance would be. So there are these general models that try to approach this some from the resource theory perspective. The general model, it includes the working body, a working system, the dimensional, cold and heat bath, and the battery system. And there are already some results. So we already know that if we allow for the joint interaction between all constituent parts of the working body, the battery, and the bath, so if we allow for global unitaries that conserve energy, and we include the battery explicitly in our description, we can actually achieve the Carnot bound. Also, if we do not allow for global operations, but we would have our working body interact with the battery first, then we will switch off this interaction, then we will switch on the interaction with the cold bath, and so on. So this so-called step fashion. But if we do not include the battery explicitly in our description, it would be some external field to which the energy is given, then again we can saturate the Carnot bound. So there are at least two questions that are emerging here. What if we have the explicit battery in our description, but we are restricted to this step fashion of working? What is the achievable efficiency of the machine, and also how it affects power? Whenever you do not have a global interactions, you are interacting solely between the working system and the battery, and of course the correlations can develop here and can influence the operation of the machine. So we propose a model of the engine that aims at giving answers to this question. And this model is that we have local operations, so separate USB, USC, and USH. These unitaries commute with the local Hamiltonians, so in this way we'll have a conservation of energy. We demand that the hot baths are in equilibrium. We also select a specific model of the battery. I will elaborate in a second. And we really restrict, for now, to the two-dimensional working body that would act in that would evolve in a cyclic fashion. So yes, this is the model. This is the first postulate. I will walk through the postulates before giving you the properties of the model. So here the fact that we separate the cycle into these steps, it means that the model is not fully autonomous. What I mean is that in order to switch on and switch off the interactions between the battery and the cold bath and the hot bath, you need some external system that would be able to implement these operations. And the dimensionality of this external system, it should be counted in as well. So it's not completely fair to say we are just having a two-dimensional working body here. No, because there is this external clock that does this job. But because these switches are reduced, there are just 3 in the cycle, then at least this is a step forward to a fully autonomous description. And in our case, there are 2 cases of these strokes. We have a heat stroke, which is the operation between the working body and one of the two baths. And we have a work extraction stroke, which couples battery to the working system in order to extract work. The baths are taken in a thermal reservoirs, in a Gibbs state, sorry. And after every cycle, the baths are refreshed. So they are taken again in the Gibbs state. This corresponds to the fact that the baths have infinite capacity, and we do not actually influence the state of the bath when we interact with it. Okay, so here in this model, the major tool that we used to solve it was the state that allowed us to describe correlations between the battery and the working system. This is the model of the battery that we also took. It is the battery here is modeled by the so-called infinite weight, which you can think about as the harmonic oscillator without a ground state. So it's an infinite ladder of levels, and we make this assumption after the work of Skrzypczyk from 2014 that the translation operator defined in this way, which just pushes the state of the system down or up, that it commutes with the unitary that acts on the battery and the system. And this commuting is enough to satisfy the second law and fluctuation relations in the classical limit. So in this way, we arrive with the proper model that does not violate thermodynamics. And also the nice property is that the change of the average energy of the battery in this case would not depend on the initial state of the battery, which is a very nice property if you want to use the battery many times. How much time do I have? Maybe 5 minutes?
Close to 4 minutes. More.
Okay, so I will speed up. So the main tool is the control marginal state, and this control marginal state is defined on this Hilbert space of the system, but it takes into account correlations that develop between the system and the battery, and this state is defined through this control translational operator that, as you see, uses the symmetry of the battery, and the idea is that we define major figures of merit, which is energy, just the average energy of the system, and the ergotropy, which is the maximal amount of energy that you can get from a state when you perform some unitary operation on it. And then we will use these figures of merit in order to describe the whole operation of the engine. So based on this state of the control marginal state, we are able to calculate the evolution of the system in the work strokes. So when we are coupled to the battery, then the same we do for the case when we are coupled to the bath. And then we do optimizations, and we can show that the second law is actually satisfied. We can also show that the whole process is irreversible in a sense that you cannot get more work from the process in this engine than the change of the free energy of the system. Actually, that you get also always less work. So we investigate the cyclic operation of the engine and also the task of the extraction of energy from the bath. And for the cyclic case, we have a full characterization of properties. So this is the plot showing how the engine works. So usually the engine would work just in this regime that the cold temperature is smaller than the high temperature. So it would work above this in this regime above this black contour, but because we have very small dimensionality of the working body, we are just limited into the area to the left from the 0 line. And also, because this is irreversible, the efficiency will be always smaller than a Carnot. Almost concluding, I would add that we also showed that the correlations cannot help. So the optimal protocol relies on extremal permutations and the so-called extremal thermal processes, and no correlation. If you have any correlations and if you want to cyclically go back to a state that has this correlation, then it would be detrimental to the power production and efficiency. We also compare with the Otto cycle, and we identify the operational regimes in which this engine actually has enough quantum properties to outperform classical Otto cycle that does not have quantum features. We have also a numerical study of correlations between the battery and the system, and my last sentence would be that whenever you have sequential charging of the battery, then there are classical correlations developed between the battery and the system that actually make the battery to be more to be squeezed around, to have lesser variance over the mean energy. So this also shows that this battery can be more suitable for future uses. This is my summary, and thank you very much for your attention.
Yeah, thank you very much for the very interesting talk. Are there any questions? Please raise your hand if you have a question, or feel free to